Hello again, calculus students, and welcome back. Today we're going to be talking about optimization problems. Optimization problems are very important in today's world. In fact, this may be one of the most important applications of calculus. Optimization problems consider questions like the following. Suppose that you have a delivery company and you'd like to know what is the most efficient route to deliver the packages. Maybe people at Amazon think about these sort of things. A CEO of a company that produces a lot of products, maybe the CEO of Sony would wonder, how many PlayStations should I make in order to maximize the profits of the company? A chemist might wonder, how much hydrogen should we put in a certain solution so that when we set it on fire, it generates as much heat as possible? The world is full of examples like this. In fact, in today's world, such problems can have hundreds, thousands, maybe even millions of variables. So today we're going to start developing techniques that are at the foundation of solving these really important real-world problems.
Hello, calculus students. Today we're going to be talking about optimization problems. So these are a kind of problem where we're trying to figure out what are the best parameters that give us some sort of maximum or minimum in the problem. So this comes up a lot in real-world situations, like a business person is trying to minimize the cost of some manufacturing process, or maybe trying to maximize the profit, or in some engineering situation, we're trying to come up with the parameters that maximize the volume or maximize the temperature, things of this nature. So let's start with some really sort of simple geometric type versions of this, and then we'll move into some slightly more advanced problems that seem a bit more connected to the real world. So the first problem here is, what two non-negative real numbers with a sum of 20 have the largest possible product? So you can think of lots of different non-negative real numbers that add up to 20, 19 plus 1, 18 plus 2, so on. But every time you multiply those numbers together, you get different products. So if you did 19 times 1, those two numbers add up to 20 and the product is 19. And then if you do 18 times 2, the product is 36. Well, that product's a little bit bigger. So we want to find the biggest possible product. So how can we approach this problem? Well, maybe it would help by introduce some variables. So maybe we'll call these two numbers x and y. So if x and y are the two numbers in question here, one thing that we know about these two numbers is that they're non-negative. So x and y are both greater than or equal to 0. And we also know that x plus y has to equal 20 in this problem. So the language we use in optimization problems is that we call this equation right here a constraint. And then what we want to do is find the maximum value of the product. So maybe we'll call that product P. P equals x times y. This formula, P equals x times y, is what we call the object function. This is the thing that we want to maximize. Now at this point, our objective function has two variables, but in order to do the kind of calculus that we know how to do at this point, we need to reduce it to one variable. And typically what happens is you use the constraint and you solve for one of the variables in the constraint equation, and that allows you to reduce the number of variables in the objective function by substitution. Let's see how that goes. So x plus y is equal to 20, and from that we can deduce that, let's say y, solve for y, we get y equals 20 minus x. And so now we can substitute into the objective function, and we'll get p as a function of x. P of x would be x times y, but y is 20 minus x. So now our objective function has just one variable. And one thing you want to do once you have your objective function reduced to one variable, it's often useful to think about what the domain of that function is. Now in this particular problem, we know that x and y are both greater than or equal to 0, but also, if you think about it, if x plus y has to be 20, then we can also tell that both x and y have to be less than or equal to 20. So in particular, x, which is the variable that we've reduced that's our variable of choice in our objective function, we can see that x has to be constrained to be between 0 and 20. So now we've got an objective function P of x equals x times 20 minus x, and we know the values of x fall between 0 and 20, and endpoints included. So this is good to know because we had a method for optimizing a function whenever the variable was in a closed interval and we knew we had a continuous function. And we definitely have a continuous function here. In fact, we have a differentiable function. So let's use what we know about how to find the maximum or minimum of a function on a closed interval. The process was find all of the critical points that are on the interior of that interval, and then plug the critical points that you find in the interior of the interval and the endpoints of the interval into the function and just see what's the largest and smallest values. In this case, we're mainly interested in the maximum value of p. Okay, so p prime of x. I think to make life a little easier, I'll just go ahead and distribute the x on p of x so that it's 20x minus x squared. So that instead of using the product rule to get the derivative, I'll just differentiate it where it's in the form 20x minus x squared, and I'll get the derivative is 20 minus 2x. And then if I want to find the critical points, and I'm only interested in the critical points in the interval 0 to 20 in the interior of our domain. So then I'll do 20 minus 2x and set that equal to 0. Notice that the derivative is never undefined, so I don't have any critical points of where the derivative is undefined. And solving for x there, I think you quickly see that x is equal to 10. And that is in the interior of our interval, so that's good. So at this point, I got one critical point, and then I have the endpoints, 0 and 20, and I'm going to plug the endpoints. So I'll look at p of 0 and p of 20, and then I'll also look at p of 10, and just see what's the biggest value. Well, p of 0, you can see from the definition of p that we get 0 there. We also get 0 whenever x is equal to 20, because that means y is equal to 0, so the product's 0. And then p of 10 will be 200 minus 100, so that's 100. So now we can answer the question. The maximum value of p is 100, which happens when x is equal to 10. And then, of course, we can also say what y has to be. If x is equal to 10 and then the two numbers have to add up to 20, then we got to have y is equal to 10 also. So this example, which is pretty simple, illustrates pretty well the methodology that we have to use. So we can kind of go back through and look at what some of the steps were. We needed to have variables to represent the quantities involved in the problem, sort of at the beginning. And then we need to identify the constraints in the problem. The fact that x and y had to be non-negative was a constraint, and the fact that x plus y had to equal to 20 was a constraint. And then we had to identify what function we were trying to optimize. And in this case, we were trying to optimize the product, p, which was x times y. And then, as is usual in these type of problems, we use the constraint or constraints to reduce our objective function down to where it just has one variable, and we also try to identify an interval on which that function is defined. And then, from there, we use methods that we previously learned to optimize the function in question. So it usually involves taking the derivative, finding critical points, and if we have a closed interval, we can use the method for optimizing problems on closed intervals that we learned. And there will be other situations arise where we don't have a closed interval, like 0 to 20. Sometimes you have an infinite interval, but if you find that there's just one critical point, then you'll know that you have an absolute min or max at that critical point. So let's try another problem. But first, let's have a look at a sort of set of guidelines for doing these kind of problems. So guidelines for optimization problems. Most of this stuff is pretty common sense, but it's still helpful to pay attention to it all. First thing you want to do is read the problem carefully, identify the variables, and possibly draw a picture if that makes sense. The second step is to identify the objective function. That's the function that you're trying to optimize. Either find a mixed maximum or a minimum of that function. And then you want to write that function in terms of the variables of the problem. And at this point, your objective function may be a function of more than one variable. Third step, identify the constraints. And of course, you want to put those in terms of the variables in the problem. And the fourth thing you typically do is use the constraint or the constraints to eliminate all but one variable in the objective function. And then you've got the objective function, step 5, expressed in terms of a single variable. You want to identify what's the domain of that function. In other words, what's the interval of interest. Sometimes you have to use common sense restrictions on the variable. Like if you're doing something that involves distances or lengths, you know that you can't have negative lengths. So you may restrict the variable to be greater than 0 or something along those lines. But you do have to find an interval of interest for the function. And then at the sixth step is use what you already know about calculus to find the maximum or minimum. All right, so let's take a look at this next problem here. And let's try to apply these 6 guidelines. So in this problem, we have a rectangular pin that's going to be built, and one of the sides of the pin is going to be against an existing barn. So we get one wall of our pin is for free. Now, we have 200 meters of fencing that we have to make this the other 3 sides of this pin. One of the sides being the fence, the wall that's already there. So the question is, what dimensions will maximize the area of this pin that we want to build? Bet you didn't know farmers had to do calculus. Okay, so let's draw a picture of what's going on and try to get some variables involved and that sort of thing. So we've got a big barn here. I'm just going to draw a red line here to represent the barn. And we're going to build up a pin up against that. And of course it's going to be a rectangular pin. So our pin's going to go out here like in blue here. And we know that we have 200 meters of fencing to do this. Let's put some variables on the sides of this rectangular pin. Maybe we'll call this side down here X, and then these other 2 sides will have a length of Y. I can't think of any other variables that we would need to introduce into this problem. So what's our constraint here? Well, we only have 200 meters of fencing as the main constraint. So in terms of that picture, we can see that the amount of fencing that we're going to need to use is X plus 2Y, and that has to equal 200, the amount of fencing that we actually have. Now, of course, we could make note that X and Y both have to be greater than or equal to 0. If either one of those variables was equal to 0, of course, we wouldn't have a pin at all. Just have a straight line of fencing. But I guess that's at the edge of what could happen. And certainly, I don't think you could certainly say X couldn't be more than 200. Just these are some things you want to kind of keep in mind as you're thinking about it. Now, what's our objective function? Well, that's the thing that you're trying to maximize or minimize. In this case, we're wanting to maximize area. So an area function here, well, the area of that pin would be X times Y. So now let's try to reduce our objective function to one variable. Well, I can see from the constraint that X plus 2Y is equal to 200, that X is 200 minus 2Y. And now I'm going to substitute that into the objective function A. So A as a function of Y will be 200 minus 2y multiplied times y, which I'm going to expand out to 200y minus 2y squared. So there's my objective function. A of y equals 200y minus 2y squared. And also I want to think about the interval I'm working on here. Well, I can see that since I only have 200 meters of fencing, and I'm using 2 copies of y to make this pin, that certainly y couldn't be more than 100. If y were 100, then we'd be using 2 copies of y, so that's 200, and there you've used all of your material. X would be 0 in that case. So I can see that this function is defined on the closed interval 0 to 100. Okay, so that's good to know. Here I've got a good continuous differentiable function on a closed interval, and I know how to maximize those type functions. I just have to find critical points that occur in the interior of the interval, plug those and the endpoints into the function, see what's the biggest value. So let's do it. Let's find our critical points in our open interval from 0 to 100, if there are any. We look at a prime of y. A prime of y would be 200 minus 4y. And to get those critical values, I have to figure out the places where the derivative is either undefined, which never happens, or equal to 0. So a prime of y equal to 0 would give us 200 minus 4y equals 0. And I think from there you can pretty quickly see that y has to be 50. So that does happen in the interior of our interval 0 to 100. So now we've got to look at a of 0, a of 100, those are the endpoints, and then a of 50 and see what's the biggest and smallest. A of 0 I see is 0. A of 100 I also see is equal to 0. A of 50, what do we get there? Well, that'd be 200 minus 100, so that's 100 times 50. Well, 100 times 50 would be 5,000. And this would be in meters cubed, or meters squared. So we can see that the dimensions maximizing the area are, well, we know y has to be 50. And if y is 50, how do we figure out what x has to be? Well, remember our constraint formula. I could just take y equals 50 and put it in up here. And so if y is equal to 50, then x is going to be equal to 100. Okay, that seems reasonable. Okay, so in this next problem, this is a basic geometric problem, but I wanted to do a problem where you don't end up with a closed interval. And so what do you do in those cases? So in this particular problem. It's just a geometry problem. What point on the line y equals 3x plus 4 is closest to the origin? So we should be able to pretty quickly draw a little picture for this. Okay, so here's a picture of the line. We can see that it has a y-intercept of 4 and an x-intercept of negative 4/3 that we get just by putting in y equals 0 and solving for x. Now we want to find the point on this line that is closest to the origin. Now we could check this, we could get the answer for this without using calculus, because I would know that the shortest distance from the origin to that line would be at a right angle, and so we just have to find the equation of the perpendicular line that goes through the origin and then find the intersection point of those two lines. But we want to do it the calculus way, just as to build our chops. So let's say I just take an arbitrary point on this line. Let's call it x comma y, and I could look at the distance between x comma y and the origin. Let me call that distance there little d. Well, the origin has coordinates 0, 0. So let's try to write down what are our constraints in this problem. The fact that our point x comma y has to be on that line is the main constraint here. Y is equal to 3x plus 4. And our objective function, well, this would be d. And how do you calculate the distance between x comma y and 0, 0? Well, that would be the square root of x squared plus y squared. Now, I think we could probably work with the square of the distance if we wanted to make life a little easier, but I think I'll just leave the distance, our objective function d, as it is. One thing I want to think about is I got to reduce the objective function down to one variable. But we can see that from the constraint, y is already set equal to 3x plus 4, so let's just substitute 3x plus 4 in for y there, and so we're going to end up with d as a function of just x is the square root of x squared plus 3x plus 4 quantity squared. And I might try to think about an interval on which this function is defined, but really the value of x could be anything, because as x comma y ranges along that blue line in the picture, the value of x can go from negative infinity to positive infinity. So this is just we really don't have any way to restrict the variables, so our interval is the whole real number line here. So let's see what we can do with this. D prime, so basically I want to find critical points. So let me look at the derivative. So the derivative here would be, well, that's bring down the 1/2, reduce it by 1, then multiply times the derivative of the inside, which would be 2x, plus 2 times 3x plus 4 to the 1 times 3. Maybe I'll make this look a little nicer. I could pull a 2 out and then cancel with the 1/2, and then I'll have 10x plus 12, all divided by the square root of x squared plus 3x plus 4 quantity squared. So just simplifying my derivative there a little bit. Now I ask myself, are there any values of x that would make this thing be undefined? Well, the answer is no. There's no way to make that denominator equal to 0. X squared plus 3x plus 4 quantity squared is always greater than 0. So the stuff that's inside the radical is always positive, so the denominator is always positive here. So the only way that this thing will be equal to 0 is if the numerator is equal to 0. And so finding the critical points just boils down to setting the numerator equal to 0 and solving. So the critical point that I'm finding here is x equals negative 12 over 10 or negative 6/5. Now there's only one critical point. So if we would examine the sign of the derivative, so I'm going to look at the sign of d prime. There's only this one critical point here at negative 6/5. If I plug some value to the left of negative 6/5 into d prime, for example, let's say I plugged in negative 2, that's a test point. Well, just think about plugging that negative 2 into this derivative here. It doesn't matter what you get in the denominator. We know the denominator is positive, but in the numerator you'd get negative 20 plus 12. That's negative, right? So the sign of our derivative is negative here. And then if you put a number to the right of negative 6/5, let's say 0, into the derivative, you can see in the numerator the derivative is going to be positive. So you can see what the function is doing here. the function's going down, and then it starts coming back up at -6/5. So you can just see, and since there's only one critical point, that's an absolute minimum of the function right there. So from this we see that d is minimal when x is equal to -6/5. Let's see if we've answered the question. It says, what point on the line is closest to the origin? So what we've got is the x-coordinate of the point. So the closest point on y equals 3x plus 4 to the origin 0, 0 is -6/5. And then what's our y-coordinate there? Well, let's see. Do a little scratch work here. Y equals 3 times -6/5 plus 4. What does that work out to be? -18/5 plus 20/5, I guess. So that would be 2/5. So that's pretty cool. We could check our answer here. This is one of those rare instances where I can get the answer an alternative way. So one way to get that same answer is, I mentioned it at the beginning, all we'd really have to do is find the equation of the line that's perpendicular to the given line that goes through the origin. Well, that original line has a slope of 3, so the perpendicular line would be y equals -1/3 x. See, because the perpendicular line has the negative reciprocal slope, and then if it goes through the origin, I've got a y-intercept of 0. So anyway, this is the equation of the perpendicular line, and then you just check and see where those two lines intersect. So -1/3 x would need to be equal to 3x plus 4, and when you solve for x here, you get, let's see, subtract 3x from both sides, and you get -1/3 x minus 3x equals 4. And so on the left hand side there, that'd be -10x over 3 equals 4. And from there you get x equals -12 over 10, which is -6/5. Check it out. That's the same value of x. So yeah, it checks out. All right. It's good to know when your calculus is working good. Okay, so now let's do a couple of examples that are a little bit more realistic, but usually what comes with more realistic is a little bit more complicated as well. Okay, in this example, we're going to pretend that we're some sort of company that makes shipping boxes. And we're going to make a square-based shipping box, and we need it to have a certain volume, 16 cubic feet. The material that we're going to use to make the box, well, on the stuff that you're going to make the base costs twice as much as the stuff that you're going to use to make the sides. And then the material that you're going to use, the top, only costs half as much as the material that you're going to use to make the sides. So then the question is, what dimensions minimize the cost of this box that we got to make? This is kind of complicated. Let's just start trying to draw a picture and see what we can do with this thing. So the thing that I'm going to use is a square-based box. So let's see. Okay, so here's my box. Now, it has a square base, so that means the top of it's going to be square too. Let's say the dimensions of the base are x by x. And then the height of the box, let's say, is y. So I think we've got the dimensions of the box here. Now, quickly we can see what our objective function is. Our objective function is, I'm sorry, not the objective function, a constraint here. So we can see our constraint. Remember, the box has to have a volume of 16 cubic feet. But I can also see that the volume of this box is x times y. So we have x squared y has to be equal to 16. Now, I can say that, x and y both have to be positive here. Neither x nor y could be 0, because that would give you a volume of 0. So maybe I'll just make note here that x and y have to be positive. But I actually can't find any maximum value for x or y. I mean, if x could be really tiny, in that case y would be extremely large, or y could be really tiny, and then in that case x and y would have to be really large. So all we know is that x and y have to be positive. Okay. So now our objective function is the cost. So how do we figure out the cost here? Well, I don't actually have specific dollar amounts for how much the materials cost. I just know their relative costs. So I know that the material used to make the base costs twice as much as the material on the sides, and then also the material at the top is half as much as the cost that it makes, on the sides. So maybe we'll let the cost of the sides be sort of the base. Like, let's just pretend, I guess we could put in a number, but it doesn't really make a difference what the cost is for the sides. The top stuff is half as much and the bottom stuff is twice as much. So we could just pretend that, it costs $1 per unit area to make the sides. So the cost function would be, let me just put a blank here, and then 4xy is the area of the sides. There's 4 sides and they each have area x times y. And then we've got something, and then we got the area of the top. The area of the top is x squared. And then we've got the area of the bottom, which is also x squared. So I'm putting little blanks here for coefficients in front of these things. So if we were to pretend that the sides cost $1, then the top has to cost $2. The bottom costs twice as much, so $2 per unit area on the bottom, and then 1/2 for the top. I mean, I could just put some letter there like A, but it's going to not really matter in the end because it'll end up just sort of canceling off as we do the math. So I think we can write our cost function like this: 2x squared plus 1 times 4xy plus 1/2 times x squared. That was probably the trickiest part of this whole problem, was just figuring out how to capture the objective function. But now that we have an objective function, you notice that it has 2 variables, and we have to reduce that to 1 variable. So we can see from this constraint that we could easily solve for y. Y would be 16 over x squared. So if we substitute that into the cost function, we can get the cost function down to be a variable, or in terms of the variable x. So the cost function of x would be 2x squared plus 4 times x times 16 over x squared, when you solve for y in the objective function there, or in the constraint function, and then plus 1/2 x squared. And maybe we'll just simplify that a little bit. C of x equals 2x squared plus 64 over x plus x squared over 2. Okay, and what's the domain of this function? Well, as we discussed previously, all we can say is x has to be positive. So this would be on 0 to infinity. All right, so let's calculate the derivative. C prime of x will be 4x minus 64 over x squared plus x, or 5x minus 64 over x squared. And then we want to find critical points in the interval from 0 to infinity. And so you can see that the derivative is undefined when x equals 0, but we don't care about x equals 0. It's not in the interval that makes sense in this problem, so don't worry about that critical point. And then you can set the derivative equal to 0 to find the other critical points. So we take 5x minus 64 over x squared, set that equal to 0. I think I'll multiply both sides of the equation by x squared, and I'll get 5x cubed minus 64 equals 0. And then solving for x here, I'd get x equals the cube root of 64 over 5. And the cube root of 64 is 4. So this just works out to be 4 over the cube root of 5. And that is in our interval 0 to infinity. Okay, so let's figure out what's going on at this weird critical value of 4 over the cube root of 5. So let me draw a number line representing our domain here. Our domain starts at 0, so let me do like that. And then here's 4 over the cube root of 5. And then I want to plug in some number that is to the left of this and some number that's to the right for test points. Well, the cube root of 5 is certainly less than 4. So I think if I put 1 in here, that would be a number to the left of that. So I'm checking the sign of the derivative here, okay? So I'm checking the sign of c prime. So if I plug 1 into the derivative, I see that I get 5 minus 64. That's definitely negative. So the test point of 1 gives a negative derivative. And then if I plug in something to the right of that value, what would be something to the right? I don't know, how about 10, just to be safe. If I plug 10 into the derivative, c prime, I'd get 50 minus 64 over 100, so that's 50 minus some small number. That's positive. And again, this is one of those situations where you just have one critical value, and so if it's a local maximum, it's also going to be an absolute maximum, or if it's a local minimum, it's going to be an absolute. This one's going down, and then it's going back up, so this is an absolute minimum happening here. So what we can see from our sign check of the derivative is that c has an absolute minimum at x equals 4 over the cube root of 5. And so let's try to answer the question as it was asked. The question was, what dimensions minimize the cost? Well, I know what the value of x is, so I need to find the value of y. But I can use that constraint formula to figure out what the value of y would be. The cost is minimized when the box has dimensions 4 over the cube root of 5. And what were our units in this problem? Feet. Feet by, so it was x by y was the box. So there's the x by the x, and then the y, let me just remember that constraint formula of x squared y equals 16. So just a little scratch work over here. X squared y equals 16, so y is equal to 16 over x squared. So that'd be 16 over 4 over the cube root of 5 squared. So actually you're going to get 16 over 16, and then you get 5 to the 2/3. So it'll be by cube root of 5 squared feet for the other dimension. So that's how I got the third dimension there. So the answer turned out to be a little bit odd. I was a little concerned about that because you always expect these problems to somehow work out magically to whole numbers, but I did check the work and this is the correct answer. So there you have it. Don't expect always to have even whole numbered answers for everything. And if it's a real world problem, you certainly don't expect that. Alright, so now you see, these problems get a little harder when they start trying to represent real world situations. Just parsing the language of the problem sometimes takes a little bit of work to do. So you have to give yourself plenty of time to do these problems. Don't expect that you're going to do one optimization problem per minute or something like that. It might take you 10-15 minutes to knock one of these out. It might even take you 30 minutes to knock one out. So give yourself plenty of time to do these. We'll do one more example of one of these more complicated real world problems here. In this situation, we've got an island that is 3.5 miles away from the shoreline. And then somewhere along that same shoreline is a power plant. And you want to run an electrical cable from the power plant out to that island. But the problem is, the complicating factor here is that it's more expensive to run underwater cable than it is to run cable along land. So you might think, well, I'll just run a cable straight from the power plant that's on the shoreline out to the island, so all of the power line would be underwater. But it might be cheaper to run the power line down the beach a ways, and then at some point down the beach from the power plant, turn the cable and then go underwater. So in this particular problem, the power line, when you're running it underwater, it costs $2,400 per mile to run it underwater, but it only costs $1,200 per mile to run the cable along land. So then the question is, at what point should the underwater cable meet the land to minimize the cost? So let's try to draw a picture of what we got going on here. So here's my island. I only know one way to draw an island, and it has to look like this. There's my palm tree with a small coconut in it. And then here's the shoreline. And then here's my power plant. There is bad stuff coming out of those pipes from the power plant. And then the island here is 3.5 miles from the shoreline. And we need to run a cable, partly over land possibly, and partly over sea. The cable here in red might go something like this. Oh, and by the way, we know that in the problem, it states that the power plant is 8 miles along the beach. like this. So that distance there is 8 miles. So we want to minimize the cost. And we know that, this leg of the cable out here that's underwater costs $2,400 per mile. And along this leg of the beach, or the land part of the line, is $1,200 per mile. Well, if I want to start putting some variables on things, maybe we can just let the beach be sort of like the x-axis, and we could call this point 0. The point closest, the point on the beach that's closest to the island there, that'll be 0. And this point where the cable meets the land, let's call that point x. So one thing, I see a right triangle here, so that's interesting. Maybe I can do something like that. Let me call that red part of the line that's out in the ocean y. Now the part that the red part that's along the beach, I can see that must be 8 minus x, just because the picture there, the distance from 0 out to the power plant is 8. So I can just subtract from 8 to get that distance on that red bit. So I think I'm starting to see something here. So one constraint I see is going to be forced by that right triangle there. I can see that the bottom side of this little triangle right here that I'm shading, the bottom side has length x, and then there's a hypotenuse of y. So I can see x squared plus 3.5 squared has to equal y squared. And the objective function, well, that's the total cost to lay this cable. And so that cost would be, well, it's $2,400 for each mile of the y type, and then it's going to be $1,200 times the next part of the cable, which has a length 8 minus x. And like usual, our objective function has 2 variables, so we need to reduce the number of variables here. And we could certainly do that because in the constraint function we could solve for y, and since everything has to be positive, we'd see y has to be the positive square root of x squared plus 3.5 squared. So x squared plus 3.5 squared equals y squared. From there we get y has to be the positive square root of x squared plus 3.5 squared. And I don't have to worry about the negative root because, y has to be non-negative. It's the length of a cable. So then from there we can reduce the objective function down to be a function of x. So c of x will be 2,400 times the square root of x squared plus 3.5 squared plus the 1,200 times 8 minus x, which I think I'll prefer to write it like this. I'm going to go ahead and distribute the 1,200 and write it as 2,400 times the square root of x squared plus 3.5 squared minus 1,200x, and then plus 96,000. And also, I can see just from the problem in the picture that x there has to be between 0 and 8. X could be equal to 0 and x could be equal to 8. If x is equal to 0, that just means that you're going to run the cable all the way over to the point 0 on the picture and then straight out to sea 3.5 miles. Or if x is equal to 8, that means that all of the cable is going to be underwater. So this is on closed interval 0 to 8. I can see. Okay, great. So now we've got a closed interval problem. We know how to solve those. We just find the critical points that are in the interior of that interval, and then plug those critical points and the endpoints into the function and see what comes out the biggest. So c prime of x, well, let's see, what do we got here? So we got 2,400 times 1/2 times x squared plus 3.5 squared to the negative 1/2 multiplied times 2x, derivative of the inside function, minus 1,200. Okay, and then simplifying the derivative here a little bit, you end up with 2,400 times x divided by the square root of x squared plus 3.5 squared minus 1,200. And if we want to find the critical points, we want to find those in the open interval 0 to 8. First of all, just notice that the derivative here is never undefined because what's inside that radical, x squared plus 3.5 squared, is always positive. So we don't have any critical points where the derivative is undefined. So we just need to set the derivative equal to 0 and solve for x. So do 2,400 times x over the square root minus 1,200 Set that equal to 0. Well, if I would multiply both sides by that radical and then divide both sides by 1200, I'll get 2x minus the square root of x squared plus 3.5 squared equals 0. And then I could move the radical to one side, leave the 2x on the other, and then square both sides. And you'll end up with 4x squared equals x squared plus 3.5 squared. And from there you can write it like this. 3x squared has to equal 3.5 squared. And from there you get that x has to be the square root of 3.5 squared over 3. Or I guess I could just write that as 3.5 over the square root of 3. Okay, so that's my one critical point in that interval, and I can tell that that is in the interval 0 to 8. It's certainly positive, but it's certainly not bigger than 8 either. Okay, so then you just got to plug these numbers into the derivative. This is kind of an odd number to have to plug into we have to plug those values in. We have to plug 0, 8, and this one critical point into the original function. And it's sort of a strange number to plug into the original function. So I'm going to get the computer to compute those values for me. So let me do that real quick. Okay, having plugged the three numbers, 0, 8, and our square root of 3.5 squared over 3 into the original function, I see that the minimum value here happens at our critical value, because there the cost was only $16,874.61, whereas it was $18,000 if you went with 0 on X. So that would be use as much of the land as you can and then go straight out. Or if you used all underwater, it would be like close to 21,000. The answer to the question is this value of X. The question was, at what point should the underwater cable meet the land to minimize the cost? So in terms of our picture, it should meet the land at this point. 3.5 over the square root of 3, and those units there are miles. Okay, I think I'll stop there. So these problems I think you'll find are challenging, but they're kind of fun, and they really show you how calculus can really be useful. This is only the kind of optimization problem that involves one kind of variable. In the real world, there will be optimization problems that involve lots and lots of variables, sometimes even like thousands or millions of variables, and there are more advanced techniques for solving such optimization problems, but they essentially come down to the same kind of thing that you're doing here, using what you know about derivatives to sort of find these special places where the functions peak or have valleys, valley bottoms. Talk to you again soon. Bye.